Welcome to the first part of lecture 18 on graph theory. So, in this lecture we learn graph coloring. More specifically, today we will talk about vertex coloring. So, we need to color the vertices of the graph with different colors such that no two adjacent vertices get the same color. And the optimization problem here is to color the vertices with minimum number of colors. Okay, so let me start with the formal definition of vertex coloring. So, definition: if G is a graph without loops, then G is k colorable if its vertices can be colored with k colors so that adjacent vertices have different colors. So, this is what the vertex coloring is, and the graph is k colorable if you can color the vertices with k colors, subject to the condition that adjacent vertices have different colors. Okay, so let me give one example, small example. This is a arbitrary graph, and I want to color them with minimum number of colors, of course. That is the optimization problem here. So, if I color this vertex say red, I can't color these vertices red. I can't color this one red, this one red, and this one red, because these three vertices are adjacent to this vertex, and adjacent vertices must have different colors. So, I can only color, but I can color this vertex by red colors, by red color. Okay. Because these two are not adjacent. Let me take then another color, say blue color for this vertex. Just write blue in case the color is not clear. So, for this vertex, then I can't use blue or red, I have to use some other color. Let me use the green color here. So, this is green, this is red and red. and now you look at this vertex. This vertex is adjacent to a red vertex, a blue vertex, a green vertex. So, I can't use blue, red or green for this vertex. I have to use some other color, say yellow color, y. Okay. So, I have used 4 colors to color this graph. So, this graph definitely then G is 4 colorable. Okay, then the question is, can we color this graph with less than 4 colors? Is it possible to color this graph with 3 colors? That we will check. So, if G is k colorable, but not k minus 1 colorable, then we say that the chromatic number of G is k. Okay. So, k is the minimum number of color that is required to color the graph G, and notation for this one is chi G, the chromatic number of the graph G is equal to k. So, the question is, I said that whether this graph can be colored with 3 colors. If it is not possible, you need minimum 4 colors, then the chromatic number of the graph will be 4 only. And you can see that this small graph, you can check that the chromatic number of this graph chi of G is indeed 4. You can't color this graph with 3 colors. Okay. So, we characterize the graph with chromatic number 1 can be characterized. The graph having chromatic number G is having chromatic number 1 if and only if G is null graph, then only you can color with null graph, in the sense that the graph does not have any edge, like this is a null graph, right. Then you can give the same color to all the vertices, and you need only one color. Okay. Now, chi of G equal to 2 if and only if G is non-null bipartite graph. Right. Any bipartite graph you take non-null, of course, that means there will be some edges. Then obviously, if the chromatic number of this graph is 2, because you can color one side of this bipartite graph by all red and the other side may be all blue. So, the chromatic number of the graph, bipartite graph, is 2. Okay, but there is no such characterization for three-chromatic graph. That means the graph having chromatic number 3. So, we give example of three-chromatic graph. that means the graph having chromatic number 3. Look at this graph. Even a triangle, for example. So, you need 3 different colors to color this graph, right. So, if I put red here, green here, I can't use red or green here, I have to use some other color, blue. So, the chromatic number of this graph is, say, call me G1, which is the chi of G1 is definitely 3. In fact, you take any, so this is a cycle of length 3, or you can say a triangle. You take cycle of length 5, and any odd cycle. So, this is odd cycle, this is C5 cycle of length 5, and you try to color this graph with minimum number of colors, red, and then you can put red also here, and blue, you can put blue here. But for this node, now you can't use red or blue, you have to use the third color, some other color is green. So, the chromatic number of this C5 length, sorry, cycle of length 5, this has chromatic number 3. Okay. So, another graph which is wheel graph, wheels with odd number of vertices. So, this is the graph, this is say odd number of vertices, W7, 7 vertices. So, this W7 can be obtained from C6, that means you start with a cycle of length 6, and then you make every vertex and join each vertex of this cycle to a central vertex, right. So, this is what the wheel graph, wheel of with 7 vertices. Now, you try to color this graph. Of course, here you can put red, 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 and then you put blue here, blue here, blue here, no problem. You can see till now all the adjacent vertices got different, adjacent vertices have different colors. But now for the central vertex, you can't use red or blue, you have to go for the third color, green. So, that is why the chromatic number of W7 is equal to 3. Okay. Now, we give example of 4-chromatic graphs. So, wheels with even number of vertices are having chromatic number 4. So, since it has even number of vertices, you start with the odd cycle, say for example, you start with C5, and then join every vertex with the central vertex. So, this is W 6 wheel with 6 vertices. Now, you try to color this one, maybe red here, and then you can use red here also. That is all. Now, next you have to use another color, blue here, you can use blue here, no problem. But for this vertex you can't use red or blue, you have to use another color, green. And now, for the central vertex you can see that you can't use red, green or blue. So, you have to use the fourth color, say yellow, right. So, you can see the chromatic number for any wheel of with even number of vertices having chromatic number 4. Okay, so, these are the some. So, you have a clear idea about what is vertex coloring. So, you have to color the vertices of the graph in such a way that adjacent vertices get different colors, and you have to color the vertices with the minimum number of colors. That is the optimization problem here. Okay. Next, we see some result, say proposition. They are not so difficult if H is a subgraph of G, then the chromatic number of H is less than or equal to the chromatic number of G, which is quite obvious. If you can color this graph with 4 colors, then you take any subgraph of this graph that you can color with 4 or less than 4 colors, which is quite obvious. Okay. Now, proposition two, that the chromatic number of a graph G is if the graph is disconnected graph, you sort of if the graph is disconnected, then it has many components, and you color each component separately, and the maximum number of colors that you need to color one particular component is the chromatic number of the graph. Okay. So, chi of G is the maximum of you compute the chromatic number of different components and take the maximum, right. So, C is a connected components of G. Okay. So, this also is easy, we are not going to prove this one, and some special graphs like Kn, it is a complete graph with n vertices, then the chromatic number of k n complete graph with n vertices. So, suppose you have a complete graph with 4 vertices, how many colors you need to color k 4? It is easy to see that you need 4 colors to color k 4, like all the colors will be different. Okay. So, if it is red, you have to use different color for the other vertex, and similarly for this one you can't use red or blue, and finally for this one also you have to use a different color. Okay. So, chromatic number of k n is equal to n. Now, we learn we talk about basically bounds. So, we learn what is a clique. So, a clique in a graph, a clique is a subset of vertices of an undirected graph such that every 2 distinct vertices in the clique are adjacent, right. So, if I take the example that I took at the very beginning. So, in this graph, if I label them say A, B, C, D, E, a clique is a subset of vertices such that every 2 distinct vertices in that subset are adjacent. So, definitely C, which is like consist of A, B, D and C, this is a clique because you can see that these 4 vertices they are adjacent to each other. So, that is form a clique, and also B, D, E is also a clique because these 3 vertices they are adjacent to each other. Okay. And the notation W or omega G is this stands for the size of maximum clique. Okay. So, in this graph G you can see that the size of maximum clique is 4, the number of vertices in the maximum clique. So, omega of G for this graph for this G is equal to 4, right. And for this graph also it is itself a complete graph. So, the clique of K 4 is 4 obviously. Now, we talk about the lower bounds for chi G. That means, what is the minimum number of colors you need, and the first result is that chi G, the chromatic number of the graph G is always greater than equal to the clique size, the maximum clique size. or size of max clique, right. Because you see in the first example here, this has a clique of size 4, this is a clique of size 4, this is in fact this is K 4, and since every two vertices in a clique are adjacent to each other, you need 4 colors to color this part of the graph, right. So, that is why for this graph G, the chromatic number will be greater than or equal to omega of G, and the chromatic number is greater than equal to 4, because this is equal to 4 for this graph, but we got a coloring with 4 colors. So, that is why the chromatic number of this graph is 4, right. Now, the other result that so sometimes this bound is good, but it could be very loose in some cases also. There are example. Now, we talk about another bound. Proposition that the chromatic number of the graph G is greater than equal to V G, the number of vertices, by alpha G. Okay. So, alpha G is size of maximum independent set. Okay. So, let we will just give outline of this proof of this proposition. Let G be colored with colors 1, 2 up to chi G. In fact, we do not use color, instead of colors we say that okay, we just assign numbers 1, 2, 3, that means this many colors you need to color graph G, that is why the chi G is the minimum number of colors. Okay. And let Si is equal to the set of vertices colored I. Okay, because so Si consists of the set of vertices which are not adjacent to each other. Let me repeat the same example again, this graph for example. This graph we took at the very beginning, and then we colored this with red. Now, instead of coloring with different colors, I can color them with numbers. So, 1 for this one, 1 for this one, that means color 1, and then I can use color 2 for this, and then color 1, 2 can't be used, I have to use color 3 here, and for this vertex I have to use the 4th color 4. Okay. So, here you can see that S1, the set of vertices which are colored 1, is these two vertices, say this is x1, x2, x3, x 4 and x 5. So, S 1 is consist of x 1 and x 3, and you can see that these two form an independent set. If you remember, the independent set is the set of vertices such that no two of them are adjacent. So, x 1 and x 3 are not adjacent, that is why you can give them the same color, right. So, this is called the color class also sometime. Sorry. Okay. Then what we can write is that every color class S I, they must be less than or equal to the size of the independent set, maximum independent set. And here you can see that the size of the maximum independent set is 2, and the color class S 2 consists of x 2, color class S 3 consists of x 5, and the color class S 4 consists of x 4. And you can see that the alpha g for this graph is equal to 2. So, every color class is less than equal to alpha g, and V g I can write V g, or the cardinality of all the vertices or the number of vertices, is equal to easy observation that sum of the color classes, and I is from 1 to chi g, easy to understand. And then this one is from here I can write this is I to I is from 1 to chi g, and I am replacing this cardinality of S I by alpha g, by upper bound. So, this is equal to chi g alpha g. Thus, what we got is that cardinality of V g is smaller than equal to chi g alpha g, which implies chi g is the chromatic number of the graph G is greater than equal to V g by alpha g. Okay. So, this is what the statement of this proposition. So, this is another lower bound, and this lower bound, of course, sometime it works good, sometime this is a very loose lower bound. We talk about one such example in the next lecture. Thank you very much.